Yep, this one's low too. All right. All right, we are ready. I don't know what page this is. Page 15. Everybody, page 15, yes? 1515. All right. So, earlier this week we did like simple probabilities, right? So, for example, what's the probability if you roll a die and you get an even number? What would that be? An even on a die? A half, right? It's 3 out of 6. There's 3 even numbers. And so that's a simple probability. It's the favorable outcomes over the total outcomes, right? And then we made the probabilities a little bit harder by talking about something called mutually exclusive. And things were mutually exclusive if there wasn't any overlap between the two groups, right? And so, for example, if I said, what's the probability of getting a spade or a queen? There's a card that overlaps between those two groups, right? And so that would be not mutually exclusive. And so we had to figure out those probabilities, you right? Yes? Is everybody good so far? All right, both of those probabilities deal with one event. So you roll the die once, what's the probability? You draw one card, what's the probability? Today, we're going to talk about where we do more than one thing, all right? So maybe you are rolling a die and drawing a card, and you have 2 events there, 2 things happening. Or maybe you're going to draw a card, and then you're going to draw another card. And then maybe you draw a third card, all right? And so these are called independent or dependent events, and there's more than one event happening. So you're doing more than one thing to get to this probability, all right? All right, what do y'all know about independent? What does independent mean? It's by itself, right? If you are independent, do you rely on anybody else? No, right? Does not rely on anybody else. If you are dependent, then what? Yeah, you need somebody or something has happened, right? You need to like rely on somebody or in terms of probability, a dependent event means that whatever happened before it will have a effect, all right? And so independent events, what's going to happen is you're going to return the item, whatever it is, you're going to return it. Gonna fix that yesterday, sorry. So I want to think about how I want to write this. So you're gonna return the item, things are independent. So each probability doesn't change all right, this board is making me mad today.
Punch it.
I'm not gonna punch it. That's gonna hurt my hand.
At least it isn't like this brown.
See, that's the problem with punching things is you end up hurting yourself and not so much the item, right? There we go. All right, so if things are independent, what's going to happen is you're going to return the item. So each probability doesn't change with other events. So you're going to have more than one event happening. These events are happening, right? So events. And the probability is not going to change based off of the other events. All right, a dependent event means that you don't return the item. Whatever it is, you're not putting it back. And if you don't put something back, then it's not the same situation that it was at the beginning, right? So if you have a deck of cards and you draw a card, and you find the probability of drawing that card, if you keep that card out of the deck and then go for another card, you have now changed how many cards are in the deck, right? And so that is dependent because however many cards in the deck depends on the first card that you pulled. Now, if you pull a card and then you put the card back in after you haven't changed anything, right? You still start with a normal deck of cards. All right, sorry for the slow start. Let's go for it. All right, so you're given a standard deck of cards. 3 cards are dealt without replacing. That is super important. You are not putting the cards back in, all right? So after you deal the first card, you don't take that card and put it back in. You just deal another card, right? and another card. So will this be independent or dependent? This is dependent because you're not putting it back in. Dependent. Yep. Right. Yep. Yep. Everybody got that? Yes. We're good. All right. Okay. That works. All right. So what is the probability that all 3 cards are queens? So how many events are happening? There are 3 events, right? 3 cards. 1 event per card. The first event, you have to get a queen. And so what's the probability of getting a queen out of a normal deck of cards? 4 out of 52. That is event 1, right? Event 1. Is everybody okay? And that's where we would have stopped in the past, right? Event 2, you have to get another queen. So how many queens are in the deck? There are now 3, right? Because you already took 1 out. There are 3 queens in the deck. How many cards are in the deck? 51. And so what you're going to see on dependent events is there's no longer 52 cards every time they're going to drop. And then the third event would be the third card, and we need that to be a queen. So how many queens? 2. And how many cards in the deck? 50. And what are we going to do with these 3 numbers, these 3 events? Yes. Multiply. Does anybody know why I multiply? Yeah, it goes all the way back to the very first day of probability. We talked about the fundamental counting principle, right? These things are going to get multiplied together. So in your handy dandy calculators, multiply away. 4 out of 52, 3 out of 51, 2 out of 50. Give me the fraction you get, and simplify the fraction and the decimal and the percent, right? You should be able to go through all of those options. You can always use one of mine. You don't have to, of course you, but
So we have to use. But it only if it's big enough fraction, it will give me the fraction of it. It just gives the decimal.
all right, so there is the unsimplified fraction, not simplified.
That's not what
That's
I
simple.
Unsimplified. I have not simplified it yet. Unsimplified. Simplified, I end up with 1 over 5,525.
Yeah.
What if you just get the simplified and don't get the original?
Say that again.
What if you just get the simplified and not the, like,
That's okay. All right, as a decimal, what is this number? It gave you an E, and you've actually seen that E before. Anybody remember what the E does?
Yeah.
What?
It's like an extra.
Yeah, it stands for 10. So whenever you see the E, all right, I'm done with this word. Y'all, I'm just going to write over here. Is everybody okay with that?
Yeah.
All right.
No,
I did that at the end of the broken credit.
All right, and then it has this little E negative 4, yes? And the E is saying times 10 to the power of negative 4. So this is times 10 to the negative 4th power. And what's going to happen with the 10 to the negative 4th power? What we're doing is removing the decimal, and we're moving it to the left. This number needs to get smaller. How many spots do we move it? 4. So it'd be 1, 2, 3, 4. So you have a bunch of zeros. So the decimal will be 0.0018. You can round to 1, right? All right. And so that would be your decimal right here. Remove that so people can see. All right. And so what would that be as a percent? 0.01%. Is that right? Yeah, for a percent, you have to move it twice back, right? So it'd be 0.18%, or really close to 0.2 of a percent.
Well, I think you're missing the zero.
Oh, I'm missing a 0, aren't I?
That's why.
Oh, yeah, that would make sense.
Technically.
All right. Yeah, that was my fault. 1 0 too shy. All All right, so it'd be 0.02%. So what are the odds of getting 3 queens in a row?
Practically impossible.
Yeah, practically impossible, right? Because the lowest this number could be a 0, yes? And that's a really, really small number.
Oh, surprisingly, it happens more often than it should.
All right.
It depends on how good you are at shuffling.
Does the shuffling or how good you like? Does any of that really matter?
It depends what game you're playing.
It depends on what game.
I don't think it depends on any of that. The probability of getting 3 queens in a row is 0.02, no matter what happens. Now, if you're not using 52 cards in the deck, then your probability's changed, right? But if you have 52 cards,
You're playing spoons, let's say, and someone has all four spoons.
but we're not dealing. That's like you have a deck of cards and you're just dealing them, right?
Well, you put cards together, you don't shuffle.
All right, so here's the thing. If you put the cards together and you don't shuffle them and you don't put them in a random order, is it really a random probability then? You have essentially stacked the deck, haven't you? Yeah, if you stack the deck, isn't the whole point of stacking the deck so that you get the cards that you want as opposed to the random probabilities? Yes? Yeah, I would think so. So by stacking the deck, you no longer are talking about this probability more. This is just if I pick up a random deck of cards and it's in a random order and I go ahead and pass them out, right? The chances that I get 3 in a row, 3 queens in a row is really, really, really small.
Which is surprising because I've got no 4.
It is possible. That's the thing, right? It's not impossible. It's just really unlikely. All right, next one. The first card is the queen. What's the probability the second card will not be a queen? Ooh. If the first card is a queen, what is the probability that the second card will not be a queen? Now, this one's a little tricky. What is the probability it's asking for? It's only asking for the probability of the second card, right? It's not saying what's the probability that you draw a queen and then not a queen, right? So only the second card. So there is just one event here. Just one event. And it is the second card. So there is just one probability number that we're going to pick, and it's the second card. So what is the probability of the second card not being a queen? And it's important to know the first card was a queen, all right? So imagine a deck of cards. You take out a queen. That's already happened. Put that to the side. Okay? Queen is gone. One queen. It's gone. So we have what's left over, right? How many cards are left over? 51. And how many of those are not queens? 48. 48 not queens out of the 51 cards. So this one isn't multiple events. This is just one event, the second card. It is a dependent event, though, because this probability changed because the first card was a queen, and we just pulled it out. All right, part C. It says, if the first 2 cards are queens, what is the probability that you will be dealt 3 queens? So your first 2 cards are queens, all right? We're going to essentially stack the deck for this. You get a queen, you get another queen, all right? We just want to know the probability of the third card being a queen. So this, again, is just one event. And you're just looking for the third card. So if you have a deck of cards and you take out 2 queens, how many cards are left? There are 50 cards. And how many of those 50 cards are queens? 2. So that would be 2 out of 50. Which does simplify to 1 out of 25. So if we intentionally gave you 2 queens, we stack the deck and we're like, here's a queen, here's another queen. The probability that the third card is a queen would be this. All right, and part D, it says if 2 of the 3 cards are queens, what is the probability that the other card is? Not a queen. All right, not a queen. So 2 of the 3 cards are queens. So we're going to take care of that first. So imagine we got a deck of cards again, right? Take out 2 of them. They're queens. automatically. The third card, not a queen. So how many cards are in the deck? 50. And how many of them are not queens? 48. So once again, that's 48 out of 50. Which simplifies to 24 out of 25. Yeah, 24 out of 25. All right. We're still talking about a deck of cards. Number 2. Still talking about a deck of cards. You ready? Is this literally the same question?
No, not really.
Replace the cards.
They're replaced to dimension.
Ah, we're replacing. I didn't read that. I was just reading the probabilities. So we're replacing them. When you replace cards, what changes? Yeah, since they're being replaced, right, it is now independent. So the fact that these denominators are not 52 is going to change for us, isn't it?
Wait, when did we do the
Right here.
Just kidding.
We literally just did it.
Got it.
Yeah. All right, so part A. What is the probability that all 3 cards are queens? We are putting them back, yes? All right, so how many events are there here? There are 3, so we're going to go with all 3. First event, it has to be a queen. How many queens? How many cards? 52. Second event, how many queens?
4.
We put the first queen back. So how many queens are there?
4.
There are still 4 out of 52. And then the last event, we put that queen back in as well. How many queens? 4 out of 52. Will this number be higher or lower than not putting them back? Higher, because you're more likely to draw one, right? Probability of drawing one the second and third time is higher. By the way, what's another way I can write this? To the third power, 4 over 52, that whole thing to the power of 3. You can just cube it, right? Save you a little bit of time. So 4 over 52.
Oh, that is nice.
So simplified, here's the simplified fraction. 1 out of 2,197, which is better than the last one, yes? Almost twice as good if we replace them versus not replacing them, right? The decimal is 4.552, I'll round it, and then it has e to the negative 4th. And what does that e to the negative 4 do again? It moves the decimal to the left. How far? 1, 2, 3, 4. So it's 0.0004552. And in terms of a percent, it would be 0.045%, or you could round that 5 to a 6, right? Or 0.05%. So is it likely to happen? Probably not, right? More likely to happen than if we keep the cards not in the deck, if we hold on to them. All right. Questions about part A, independent, dependent. You see the slight differences between them? A little bit? Okay, part B. If the first card is a queen, what is the probability that the second card will not be a queen? So first card, automatically a queen, right? So this is only one event. Unlike the last one where there were 3 because you were drawing 3 cards, this is just one event. And we're going to say the first card, automatically a queen. Yes? After you draw that queen, what do you do with it? You put it back. And then you have to draw a second card. And the second card is not a queen. So how many not queens in the deck? There are 48 not queens. And how many cards are in the deck? 52. So the difference between this one and the last one is it's not out of 51, it's out of 52 because we put that one card back in. And that simplifies down, right? What is it? 24 out of 26, which simplifies to 12 out of 13.
Yeah.
12 out of 13. How likely is this going to happen?
Very likely.
Pretty likely. Think about drawing from a deck of cards. What's the chance that that one card that you get is the queen? Well, there's a lot of cards in there, right? And 12 out of 13 of each of those cards are not queens. So you could get a queen, it's possible, but you're more likely to get a not queen, right? Not a queen. All right, if the first two cards are queens, what is the probability that you will be dealt 3 queens? So the first two, automatically queens, all right? What happens when you get the first one? You put it back. What happens when you get the second one? You put it back. So now you're drawing the third one. So this is only one event. And that one event is the third draw. And that third draw, you need a queen. So how many queens are in the deck? How many cards are in the deck? 52. So this will be 1 out of 13. All right, and mine looks like it edited weird on the download. So part D says, if 2 of the 3 cards are queens, what's the probability that the other card is not a queen? So part D. So 2 of them are automatically queens, right? And so the last one, this is just one event. What's the probability that the last one is not a queen? 2 of them are already going to say those are queens. So you're going to draw a queen, put it back in, draw a queen, put it back in, right? Probably the other card is not a queen. How many not queens are in the deck at that point? 48. How many cards are in the deck? Still 52. And then you can simplify away. So the main difference between dependent and independent is whether or not you put the cards back in. So for independent, I would expect to see the denominators the same every time, right? Because if you're putting it back in the card, you're always going to have 52, right? Always 52. If it's dependent and you keep the card, you would expect the denominators to go down by 1 every time. All right. All right, let's go ahead, and flip to the back. We have some more examples. All right, so we have a bag. It has 3 red marbles, 5 green, and 2 blue. How many marbles are in the bag? Yeah, there's a grand total of 10. Is everybody okay with that statement? Yes, I would hope so. All right, it says 2 consecutive draws are made. What does it mean to be consecutive? Yeah, just one after the other. They're saying, hey, you're going to draw, and then you're going to draw another one, all right? What they're not saying is they're not saying you're reaching in and getting 2 at a time, okay? Because that would be slightly different probabilities. And then it says you are without replacing the first draw. So is this independent or dependent if you're not replacing? It is dependent. You're not replacing. So I'm going to write that. Not replacing. All right, so find the probability of each event. So we have the probability of getting a red and then a blue. So what the comma is representing is the 2 events. So the first event is drawing a red. The second event is drawing a blue. All right, so what is the probability of a red? How many red marbles are in the bag? How many red marbles are in the bag? 3. How many marbles total in the bag? 10. So the first event, the probability of that happening is 3 out of 10. The second event, drawing a blue. So you have pulled a red marble out. Does it go back in or no? No. So you have 1 red marble out of the bag. So if you go in for another one, for the blue one, how many blue marbles are in the bag? There are 2. How many total marbles? Just 9 now because we have taken out 1, right? Leaving just 9. that 1 out of 15, right? Yes, 1 out of 15. So what's the likelihood of this happening? What's the decimal here for 1 out of 15? What? 0.06? Repeating. All right, so then what would that make it as a percent? 6.6 repeating, or 6.7%, right? So what's the likelihood of this happening? I mean, not great, right? Better than the queen situation earlier, yes? Yes, but still not great. All right, next one. A blue and then another blue. So how many blue marbles are in the bag? There are 2. How many total? There are 10. Once you put your hand in and pull out one of the blue marbles, you have to do it again. And how many blue marbles are in the bag now? There's 1 left. And how many marbles total? 9. Is that 1 out of 45? All right, for a decimal, 0.021. So that would be what, 2.1%? So are you more likely drawing a red and then a blue, or a blue and then a blue? A red and then a blue is more likely. Both of them, though, still don't have great chances of happening, do they? No, not so much. All right. Ooh, both the draws were neither red or green. All right. If it can't be red and it can't be green, what colors could it be? It could just be blue. So both draws can't be red and they can't be green. So it's essentially saying draw a blue and then draw another blue, right? So that probability is exactly the same. That's 1 out of 45 as well. So neither red or green, it's a blue and then a blue. All right, and then the last one is red and then not red. So, how many red marbles? 3 out of how many marbles total? 10, and then you're going to keep that red marble, but now we need a not red. So how many not red marbles are in the bag? How many, sorry? 7. And how many marbles total? 9 at that point. 7 out of 30? Yeah. Which is, what is a decimal? Sorry. 0.23. Both repeating or just 3 repeating? Just the 3 repeating. So what, 23.3%? Yeah. That one's a lot higher than the others, yes? Still not great. That's only likely to happen 1 out of every 4 times you draw, right? To draw red first and then a not red. All right, bonus question. What if we reverse that? Bonus question. Probability that it's not red and then red. What if we reverse? Do we get the same thing? I don't know. Let's find out. So, how many not red marbles? 7 out of how many marbles total? 10. And then how many red marbles? 3. And then how many marbles are total on the second draw? 9, right? So calculate it. Do we get the same thing or no? Same thing, right? 7 out of 30, yeah. Same thing. What do you think? Kind of interesting that if you reverse it, it's the same thing, or no, not really?
It's multiplication.
Yeah, it's all multiplication / division. And by the way, with multiplication and division, does it matter the order that you do it all in? No. So any of these could have been reversed and you would have ended up with the same values. All right. Go ahead and try number 4. Same situation, but this time you are putting them back in. So same amount of marbles. Nothing changing there. But we're putting them back in. All right, I left most of it up here because all these probabilities are exactly the same, right? The main difference is that instead of not replacing, we are replacing. So let's look and see the original with the not replacing, how these numbers change. So the probability of getting a red, is it still 3 out of 10? And then the probability of a blue, is it still 2 out of 9? No, it is now what? 2 out of 10. And so that probability will change slightly, right? All right. I'm assuming you can multiply and do the rest. The probability of getting a blue and then a blue. The first blue, 2 out of 10. The second blue, 1 out of 9. No, what number changes? What was that? Yeah, it's still 2 out of 10. So the 1 out of 9 is back to 2 out of 10 because you put that blue marble back in. And I'm assuming you can do that calculation also, right? By the way, the probability of neither red or green is the same as blue and then blue, right? So that one, whatever you have here, is the same as this guy now. And then red and then not red. So the probability of a red, is that still 3 out of 10? On the first row, 3 out of 10, yes. And then not red, 7 out of 9. It becomes what? 7 out of 10. So sometimes when you replace, the numerator stays the same, or sometimes it's going to change depending on what color, right? But the denominators always went back to out of 10, because if you're putting it back in, every time you draw, you're going to have 10 marbles in the back. All right, how you doing? Questions? Any questions on that? All right, let's talk this last one. We have 2 cards from a standard deck of 52 cards without replacing. So we're keeping the cards. What is the probability the first card you are dealt is an ace? So the first one is just the probability of getting a ace. 1 card, it's got to be an ace. First card's an ace. So what's the chances that the first card is an ace? How many aces are in the deck? 4 out of how many cards? 52. This is not an independent or dependent event because there's only one event, right? Just one thing's happening. This is a simple probability. One event, one thing's happening. And you can simplify that, right? 1 out of 13 changes to a decimal, changes to a percent, all that fun stuff. All right, and then they get a little bit trickier. Probability of an ace and a jack, but this is in any order. Ooh, that any order is probably going to make this a little bit more complicated, isn't it? In any order. So the first card could be an ace or a jack, right? And then the second card has to be whatever one you didn't get, right? Yes? Whatever one you didn't get. All right. And we are not replacing. Okay, not replacing. So first event, how many ways could you get an ace or a jack? 8 out of 52. So that gives you either an ace or a jack, yes? That first one. Now the second event, you need whatever card you did not get. So let's say on this you drew an ace. In this event, you have to draw a jack, right? How many jacks are in the deck? 4 out of how many cards? 51, because we didn't put that ace back in, right? If this was reversed, and instead of getting an ace the first time, you got a jack the first time, then this would have to be an ace. What's the probability of getting an ace? 4 out of 51. So this probability here will give you an ace and a jack in any order. Kind of different, yes? It's kind of a unique probability there. And you can figure out the big fraction, percent, right? All that fun stuff. Decimal. All right, the last one, a little bit trickier. If an ace is worth 11 points and a 10, jack, queen, or king are worth 10 points, what is the probability that you will obtain 21 points with 2 cards? How many events do you have here? You definitely have 2 events, right? You're going to multiply those together. All right, one of the events you absolutely positively have to draw a ace. Absolutely has to be an ace, right? So does it matter if the first card is an ace or the second card is an ace? No. And if we were to switch them around, would that change our probability at all? Like on the red and the not red, it didn't change when we switched them. So we're going to go ahead and draw the ace first. Is everybody okay with that? Yeah. You can draw it second. What's the probability of drawing an ace? 4 out of 52. The other card needs to be either a 10, jack, queen, or king. So how many 10s, jacks, kings, and queens are in the deck? 16. There's 4 of each, and there's 4 different kinds, so 4 times 4 is 16. And how many cards are in the deck on the second draw? 51. And so you can go ahead and multiply those out.
It seems like it's more common than it actually is.
What do you mean by that?
Well, like, I've watched people play the game before. It involves it.
So that is kind of the core of blackjack there, isn't it?
Is a paint